Sam Boland is the Attitude Determination and Control Systems Engineer at the University of New South Wales Canberra Space. He has designed and developed an in-house attitude determination and control system which is successfully operating on 3 satellites. Sam.
Hi everyone, thanks Dave for the introduction. As you said, my name's Sam. I work at UNSW Canberra Space. I'm a space systems engineer there. My particular focus is on attitude control systems. Those are the systems that control the spacecraft orientation in space. I also have broader duties in systems engineering and spacecraft operations as well, particularly over the last couple of years as our ADCS has matured more. Today I'm just making some observations about satellite verification based on some of the things I've observed through our 5 satellites. These are our 5 satellites. So the first one is the Buccaneer Risk Mitigation Satellite on the top left that we did in collaboration with DSTG, and you heard a little bit about earlier today. And the next one on the bottom left is our M1 satellite. So the other 4 were all done in contract with the Australian Air Force. The M1 satellite sadly gave us the cold shoulder and didn't communicate with us once it arrived on orbit. The third one is, it's actually this satellite in the branding for the Space Power Conference. It's our Pathfinder satellite in the middle bottom. It shares all the electronics with our main M2 spacecraft and let us launch those early and verify that things were all working as expected. The M2 spacecraft were launched last year. They were launched as a joined pair, so 2 10-kilogram satellites forming one 20-kilogram one, and then in September last year we cut the wire holding them together, and they slowly drifted apart, and since then we've been flying them in formation. So there's been a general shift over the last decade or two in satellites from very large single satellites that are very expensive, and those will always exist, towards a much stronger use of small satellites in larger constellations that can achieve similar outcomes but have very different cost and risk profiles. And it kind of drives some thinking around what are the appropriate verification frameworks for that different class of satellite. One of my favourite examples to use here is around verifying end-to-end your attitude control system. So to do that, if you want to verify your system in a whole of spacecraft sense, you need to put your spacecraft on an air-bearing table, and you need to simulate the space environment, in particular the magnetic field, the sun, what the Earth would look like in that environment, and star fields potentially as well. On the left there's a setup you can buy from a company called Astrofine. It's a very good system. It's a very complex system, and so it's a very expensive system. For comparison, on the right is a satellite you can buy ready to go from a company called Nano Avionics, and you plug in your payload and they'll put it into orbit for you. If you compare the cost of these two things, it's actually not a simple answer whether it's worth spending the money on a full setup to test your ADCS, or if you need to take a different approach to verification. If your satellite's worth a lot of money, it is worth doing that. If your satellite's not worth a lot of money, you might need to rethink. So one of the strategies for doing that is to break down our system into different parts and verify those in different ways that are appropriate for those parts of our system. When we think about our ADCS as a system that includes some sensors that gets fed into a computer, and the software processes that data. The sensors go through some pre-processing and calibration in that software. It's very hard to characterize and calibrate your sensors on the spacecraft itself. You need a very expensive and exquisite light source for sun sensors, and then you either have to maneuver your spacecraft or your expensive light source. It's much easier to characterize and calibrate those sensors off the spacecraft and to build a workflow where you work on your components, you integrate those into a subassembly, you work on your subassembly, you integrate that into your spacecraft, and then you check on your spacecraft that the behaviour of your system you found on the subsystem off the satellite is the same as you're finding on. And that validates your previous work for going forward. Then we have the open question of how do we deal with those system functions that we can't just test by off the satellite on their own. And we use techniques that are becoming more common in industry 4.0 style methodologies. So hardware in the loop simulation testing is where we take our hardware, in particular the ADCS computer, that can be flight hardware or prototype hardware or engineering model hardware. We're probably in this case testing the software, and so our testing is applicable on any hardware that is flight representative. We build in interfaces to that system with the aim of having overlapping verification. So even our hardware test, we tested the part of the system that pre-processes and calibrates the sensor data. We try and inject data from an external running simulation into our system before that, so we're verifying that part of the software in both our verification and we get full coverage of the system. In this way, we can simulate the physics that would otherwise be tested by putting your satellite on an air-bearing table, generate sensor data inputs to the system, let the system do exactly what it does in space. It doesn't know whether it's in space or it's in a hardware-in-the-loop test. And then out of that, we get the determined attitude or torques that it's applying, or we can observe what the actuators are actually doing. We feed those into our simulation and we can verify the system behavior. And we need to pause and reflect there a little bit before we get too carried away replacing all our verification activities with simulation-based verification. Our M1 satellite was launched in December of 2018, and we spent about 3 months doing the equivalent of shouting into space, trying to get a response from the satellite before calling the search off. With no feedback from the system, you really have no solid evidence from which to conclude about what went wrong with the satellite and what in your verification activities needs to be adjusted. At this point, it really spurs some thinking about what are my critical spacecraft functions? What things must work so my system will be available and can provide feedback to me, and so I can keep learning and developing my systems and my processes. And so there are some critical functions of the spacecraft that we then need to verify through processes and testing that are essentially the same as what you would do for a very big, expensive spacecraft, and there's very little room to adjust these. We need to do our vibration testing. We need to do our thermal vacuum testing. We need to test our primary comms, that our link is strong enough to maintain communications and there's no undesirable interference effects. And we need to do integrated end-to-end spacecraft testing, which is where you put your spacecraft on a desk, you have a ground station, you pretend like it's in space, and you try to operate all the essential functions. There's not a lot of room to compromise on these style of verification activities. What happened with our development programs is we observed, generally speaking, your development follows a pattern of mechanical, followed by electrical, followed by software, and then operations development. And I've deliberately called that operations development. You do need to develop how you're going to operate your spacecraft. Early on in the phases, lead times on items tend to get longer. Launches tend to move to the right, and everyone's okay with that because there's lots of scary testing and development still to be done. At some point, you build your spacecraft, and it goes through vibration testing, and it goes through thermal vacuum testing. The mechanical guys are largely happy that the spacecraft's not going to fall apart in launch. The electrical guys are largely happy that in space, the avionics will turn on and function as intended. And at this point, most people want the schedule to move to the left, because the satellite looks exactly like a satellite that's ready to be launched. And so everyone gets excited about doing that. Everyone except the software team and the operations team, who are now panicking about the amount of work they have to do. What we did to address that was to implement the ability to do on-orbit software updates. Very routinely, every week, we're updating software on our satellites. That has the benefits of allowing you during your development program to delay certain features until after launch to be implemented. And it also gives you a greater tolerance for software bugs, which allows you to adjust your level of verification of some things. But you can't have any bugs that would result in a loss of your spacecraft. And that leads you down to either every time you update your software, you have to go through a very expensive testing process, or, and this is the path we took, you need a complex software architecture that enables you to do things in a safe way rapidly. When we implement the updatable software as a feature of our system, we're able to categorize functions of the spacecraft differently in terms of the level of verification we apply to them. So we still have high-risk items that must work, that we need to verify rigorously. Things like structures, thermal state, the power system, communications. But there are other things like mission functionality, ease of operations functions, which we can lower our verification level on because we have a higher tolerance for errors in those systems because they can be rectified on orbit with software updates. One of the tricks here is looking at your payload, because whilst you can update your payload software on orbit, you can't update your hardware. So you still need to have enough software to make sure your hardware is working. This presents a bit of a challenge for managing your team tasking. In general, your mission is centered around objectives that are based around your payloads or these high-level objectives. And your high-level documents and descriptions of your system won't say things like you must have a positive power budget, your structures must not fall apart during launch. This creates a particular challenge for software teams where they're likely to have a high number of parallel activities going on at the same time, and it's difficult for them to manage their task and workflow and understand their priorities and apply them well to the critical subsystems. Finally, you get to the point of doing your integrated spacecraft testing. Incredibly important part of the verification process. So you put your satellites on the bench in your clean room, you set up a ground station nearby, and you operate the spacecraft as though it's in space. Generally, you're testing some things that you haven't tested to date, such as your operations, procedures, and systems. Your ground station is often not included in previous steps in terms of its functional behaviour, not so much its performance. And then you really want to focus on testing the critical spacecraft functions, in particular the on-orbit software updates. Because we had some unexpected things happening during our later stages of verification, our test time for our M2 spacecraft was somewhat compressed. We had to make some hard decisions about what we tested. For some of our primary payloads, we had to choose we will only test the on-orbit reprogramming functionality rather than the payload itself. And there's a further justification you can make for that kind of activity because generally speaking in verification and validation, you do fundamentally the same thing. You take an image with the imager. I've used up my time, so that's my last slide anyway. I'm happy to take any questions.
Thank you. Noting that you did mention the compressed testing time frame, did you identify any opportunities to bring validation forward in the testing, any validation elements forward in the testing cycle rather than just on orbit in the environment?
I think one of our biggest learnings is we need to work out how to do more of that. The biggest challenge with doing that is every time you change your config, you have to think carefully about what testing you've invalidated and what testing you need to redo. So if you bring your validation too far forward, it's completely irrelevant by the time you're finished because your config has just changed so much, if that makes sense. But yeah, definitely we need to work out how we bring that forward and have a more integrated development approach that includes kind of the very end step testing.